Hello children, welcome back to physics class. I hope you're all doing well and ready to learn something new today. Well, in today's class, I would be explaining you an important topic in physics that is all about your energy. Yes, so in today's class, we shall discuss what exactly the energy is and its types. Generally, the energy is classified into three types. One is kinetic energy, the other is potential energy, and the combination of two is a mechanical energy. So let us get some clear idea about these types of energies. So before starting with, let us consider a small example. Let us consider two persons, say A and B. If you are comparing the energy levels of a person A with a person B, when do you say that the person A is more energetic, having more energy as compared to the person B, or when do you say that he is more energetic? Whenever the person A is capable of doing more amount of work when compared to the person B, we say that the person A is more energetic. At the same time, when a similar task is given to the two persons, the person B gets tired earlier as compared to the person A. Why? Because the person B having less energy implies as the work is being performed, the person B loses his energy very often, okay, as compared to the person A. That means work and energy are correlated. More energy, more work is being performed. Less energy, less work is being performed. So less energy, the person gets tired earlier as compared to the more energetic person. Isn't it? Okay. So, what is energy? So, the capacity or the capability of a person, how much the person is able to do work is simply said to be an amount of energy possessed by the person. Always remember children, this energy can be gained by either humans or animals by the food they eat. Okay. So, how does a person get an energy? The amount of energy can be gained either by human or animals by the intake of food. So, we get our energy or we gain our energy from the food we eat. So, now let us try to define this energy in a proper way. So, what is exactly energy, children? The ability or the capacity to do work itself is called as energy. The capacity to do work or the ability to do work is called as energy. Okay. So, it's all about your energy. Today's concept is all about your energy. So, what is the definition of energy? The capacity to do work is called as energy. So, the capacity to do work or the ability to do work is simply defined as your energy. Okay, so this is the definition. Now, let us look at the units of energy. Before that, is energy a scalar quantity or a vector quantity, children? We know that work done is a scalar quantity and hence work done itself requires some amount of energy. So, energy is also considered as a scalar quantity. So, energy is a scalar quantity. What are the units of work done? In a SI system, work done is generally measured in joules, and whereas in CGS system, it is measured in ergs. Hence, work done is measured in joules. So, hence, the SI units of energy are also joules. SI unit of energy is also joules, capital J, or erg. So, energy, always remember children, energy is a scalar quantity and the SI unit is joule, whereas the CGS unit is erg. So, always remember that. So, units are joules and the SI unit is joule, whereas CGS unit is erg. So, when do you say that body is possessing one joule of energy means whenever the body is able to do 1 joule of work, then we can say that the body possesses 1 joule of energy. Okay, and let us consider one more example where this energy is counts on. Let us consider a pressure cooker. And when the whistle of the pressure cooker blows, we can see that the food is cooked. Then how the whistle is being blown? Which creates the whistle to come upwards. The thing is that all about the steam. Okay, the steam which is kept, the steam which is being generated inside the pressure cooker having lot of energy, and this energy is used to lift the whistle upwards. Okay, so steam possesses some amount of energy which is able to lift the whistle upwards. Okay, so apart from that, let us consider the types of energies. First of all, mechanical energy. What is mechanical energy, children? The mechanical energy is nothing but the sum of potential energy as well as kinetic energies. Okay, so first of all, mechanical energy. So mechanical energy, let us represent this with letter capital M dot E. Mechanical energy is equals to the sum of kinetic energy and potential energy. So very clearly, the sum of kinetic energy and potential energy gives the total mechanical energy. And remember that the units of kinetic energy, whereas potential energy or well as mechanical energy, each equals to joules. So whatever be the type of energy, units of energy is always joules. Okay, so now let us try to understand the kinetic energy and potential energy in detail. So let us discuss in detail regarding the first one, that is kinetic energy. So what is kinetic energy, children? Well, before discussing what is kinetic energy, let us try to understand the meaning of kinetic energy. So what exactly is energy? Energy is nothing but the capacity or capability of doing work. Then what is kinetic? Kinetic is actually a Greek word. Kinetic is a Greek word. In Greek, the meaning of kinetic is motion. The meaning of kinetic in Greek is motion. Hence, the energy possessed by a body by virtue of its motion is called as a kinetic energy. I repeat, the energy possessed by a body by virtue of its motion is called as kinetic energy. So, what is kinetic, children? So, kinetic is a Greek word. Kinetic is a Greek word, and in Greek it means motion. Hence, the definition of kinetic energy can be written as energy possessed by a body by virtue of its motion. That means any body which is in, any moving body, any body which is in motion or any moving body always possesses kinetic energy. So let us consider a few examples of this. Any moving body means, let us consider a bus moving. So whenever a bus moving, what energy the bus must be having? No doubt a kinetic energy. Let us suppose the bullets are fired from a gun. So what energy does the bullets will be possessing? Of course, kinetic energy. So the moving bus or bullets, the fired bullets or water jet, some water is coming out from a pipe and also water jet, that water also flowing. Water is in the flowing. So whenever the water flows, it also possesses kinetic energy. So 3 examples I have considered. First one is the moving bus. Second one, bullets coming out of a gun. Okay, the fired bullets. And water coming out of from a some jet. So water jet. Not only this, children. So whenever a ball is being kicked, then what happens? The ball moves to some distance. So that moving ball also possesses kinetic energy. As well as whenever you will be hammering, so whenever we are hammering, the hammer will be moving on. So this moving hammer also possesses kinetic energy. Even if you see the blades of a windmill, whenever the blades of a windmill will be rotating, those blades also possess kinetic energy. So here are few examples of the bodies which possess kinetic energies. Okay, so now the factors affecting this kinetic energy. So what are the factors that affect kinetic energy, children? Factors that are affecting kinetic energy are mainly 2 things. One is the mass of the body. And next is the speed or velocity with which the body is moving. So these are the main 2 factors that affects the kinetic energy of the body. One is the mass of the body and the other is velocity of the body. So now let us try to derive the mathematical expressions for this kinetic energy. So the next step is all about your mathematical expression for the kinetic energy. So in order to derive the mathematical expression for kinetic energy, let us consider a body of mass m. Let us consider a body of mass m is initially at rest condition. How is the condition of the body? Initially at rest condition. So whenever certain force is applied on the body, the body displaces through some distance. So whenever force is applied by a body, the body displaces through some distance. So mass of the body is m. The distance moved by the body is nothing but some the distance moved by the body is some distance it is been moved. So after moving certain distance, it attains some velocity, say v. So what is the initial velocity of the body? 0. And what is the final velocity of the body? V. So you observe some change in velocities. Whenever the velocity of the body changes, we can say that the body is accelerated. So velocity changing means body is accelerated. So, okay. So now as F1 amount of force is applied on the body, some work is done. Okay, and the amount of work done in moving the body is W equals to F. Yes. Work done is equals to force into displacement. As I have just now told that as the body is accelerating, mass of the body is m and some acceleration A is produced in the body. So mass force can be written as F is equals to ma. The value of F can be written as mass into acceleration. So ma multiplied by distance. So what is the value of work done, children? W equals to mas. Now from the basic kinematic equations of Newton, from the third equation we can say that since V square minus U square equals to 2as, from third kinematic equation of Newton's, we have V square minus U square equals to 2as. But nowhere the value of acceleration is being given. So let us try to find out how much acceleration is produced in the body from the given data. So what V indicates final velocity. How much is that, children? V itself. And U indicates initial velocity. How much is the initial velocity? 0. So 0 square equals to 2. A is unknown. And here we consider displacement as S itself. So 2as. V square minus 0 square equals to 2as. Or V square is equals to 2as. We want to find out the value of A. From this, the value of A is found to be how much? V square upon bringing the remaining terms towards the right side, it will come to denominator. So the value of A is found to be how much, children? A is equals to V square by 2s. So substituting the value of A in the above equation, let us see what happens. So substituting the value of A as V square by 2s in the above equation, will get m times of A is V square by 2s times of s. So simplifying further, s and s will get cancelled. Hence you are left with the value. How much are you left with, children? First of all, based on the numerical number part, above nothing is there, 1, denominator we have 2. So first of all, let me write the number half. And the terms here, one is mass m and another is V square. Hence clearly the work done in moving the block to some distance s is found to be W equals to half mv square. And this work done is stored in the form of energy. By virtue of its motion, this work done is stored in the form of kinetic energy. Hence, the kinetic energy Ke, W itself is a kinetic energy. So instead of W, I am replacing with Ke. So Ke is found to be half mv square. So what is the formula for kinetic energy, children? Ke is equals to half mv square. I hope the concept is clear. Well, so before moving to the next concept, let us recall back some points based on the above concept. Children, in the above concept, if Ke is equals to half mv square, if Ke equals to half mv square, and let us suppose that if mass of the body is changed, in the above equation, initially kinetic energy is half mv square, and if the mass of the body is doubled, when the mass of the body is doubled, what happens to the kinetic energy? So, cases, different cases let us consider here. So, first case, if mass is doubled, then do you find any changes in the kinetic energy? Yes, of course. How much is the change in new kinetic energy? Let me represent it some K dash, which is equals to half mass. Earlier mass was m. Now new mass is doubled, 2 times of m. 2 times of m multiplied with v square. No change in v. So v remaining constant. Velocity constant. Velocity remaining constant. If the mass is doubled, the new kinetic energy equals to half times 2m into v square. So this 2, I'll bring it forward. Then if this 2, I bring it forward, then you are left with the half mv square. But what is half mv square? previous energy. Hence, K dash new kinetic energy equals to 2 times of the old kinetic energy. So, the new kinetic energy becomes double the previous energy. So, whenever mass of the body is being doubled, kinetic energy also gets doubled. Similarly, if the mass of the body is halved, if the mass of the body is halved, let us see what happens. Case 2. If mass, this kinetic energy, I represented this kinetic energy as K, children. For simplicity, I represented kinetic energy as K. So, old K equals to half mv square, new K is equals to 2 times of K. If mass is halved and velocity keeping constant. Velocity is kept constant. Let us see what happens. The new kinetic energy is equals to half as it is. Instead of m, now it will become half of m by 2 into v square. So, this half, 1, 2, I'll bring it forward. Then this 2, I bring it forward. Then what happens? 1 by 2 times of, already 1 by 2 is there, and mv square. So, this is equals to half of old K. So, whenever mass is doubled, kinetic energy also gets doubled. Whenever mass is halved, kinetic energy also gets halved. Is that clear, children? Similarly, let us see what happens if mass is kept constant and velocity is being changed. Let us see what changes we can observe. Case 3. If let us suppose that if mass is kept constant, mass being constant, and if velocity is doubled. So, what is happening? Velocity is doubled. So, mass as it is and V changes. The new kinetic energy will be equals to half of mass as it is, and velocity now instead of V, it should be 2V whole square, and this is equals to half m. 2V whole square is 4V square. Bringing the 4 forward, how much it will be? 4 times of half mv square, which is equals to 4 times of old kinetic energy. So, whenever keeping the mass constant, velocity making double, then kinetic energy becomes 4 times. 2 times velocity, 4 times kinetic energy. Okay, 4 times velocity, kinetic energy will be 16 times because square of that. Okay. Similarly, if mass, keeping the mass as constant and velocity is halved, velocity is now halved. What happens, children? Then the new kinetic energy will be equals to half of, this case, half of m into, now V is changed to V by 2 whole square. So, this is equals to half m, V by 2 whole square equals to V square by 4. This bring 4 forward, then it will become 1 by 4 times of, leftover is half m V square. So, this is nothing but 1 by 4 times of the old kinetic energy. So, velocity is doubled, kinetic energy becomes 4 times. Velocity is halved, kinetic energy becomes 1/4 times. So, these are the points you need to know, children. So, based on that, we have to solve so many numericals based on the same concept. Okay. So, few more applications will be there if it is clear to you. So, this is all about your kinetic energy. So, now let us move to the next one, that is